All right, we are going to have a look at how we calculate the mechanical advantage for an inclined plane or a ramp. We use a ramp to push things up, but I'm talking and writing at the same time. Inclined plane. We use a ramp to lift things, right? To get them to a higher place. And so that's kind of what we're trying to do. So we're going to compare inclined plane or a ramp. We're going to compare the lifting straight up without a ramp to what happens when you use the ramp. So if I draw a little ramp here like this, okay, and let's just put some numbers on our ramp here for a second so we can use them. Let's say that this part of the ramp is 3 meters high. And let's say that the ramp itself all the way along here is 6 meters. It's longer. And that's because if you want to lift something straight up in the air, let's say you have a box here or something, and you want to put it up here on this shelf. Well, there's two ways to do it. You can lift it straight up and drop it on the shelf. You will push against the force of gravity, but that's going to require a certain amount of force, right? The other option is to put a ramp here and slide it this way up the ramp. But you'll notice that's a longer distance. It's always going to be a longer distance than just lifting it straight up. And so remember, when we talk about effort force and effort distance, load force and load distance. Now, sometimes we use an R for distance, like you did with torque and levers. Sometimes we use a D, and there's a reason for that. With things that seem to be turning, the R stands for radius, right? But it still is just a distance. Whereas on a ramp, nothing's actually turning or spinning around. There's no torque involved, really. So we're not using torque equations, but we still are looking at the relationship between the force that we exert and the distance that we are pushing it through. So when we look at this here, whoops, I see I put an E there, and that should be an L. Let's fix that load. Sorry. Okay, when we look at this little thing, we see that there's a relationship. So if you make the effort distance right here get bigger, then the effort force it can get smaller without losing anything. You can still have the same amount here when you make one smaller and one bigger. So we're making the effort distance right here larger to hopefully reduce the effort force. But we're still going to achieve the same thing. Whether you lift straight up or use the ramp, you basically get this block or this thing that you wanted down here. You get it from here up to here. That's the end result. So that's what we're going to look at. So we have a ramp here, and we say it's 3 meters up. So that's how high the object is going to be when it's finished, when we get it to the top of the ramp. But to do that, we're going to have to push it 6 meters along the ramp. See, extra distance, but that means less force. So let's imagine then what would happen, or let's look at what would happen for the IMA, the ideal mechanical advantage. Well, in this case, we know that the ideal mechanical advantage is a ratio of the distances. It's the effort distance compared to the load distance. In the case of an inclined plane, the lifting up is what we would call the load. That's what we mean when we're referring to the load. That would be if you just lifted this thing straight up, how high would you have to lift it? Well, you'd have to lift it 3 meters up. So the load would be lifting without the ramp. Whereas the effort refers to what we're doing here. We're lifting all the way, we're pushing more or less all the way up the ramp. And so what you have here is an effort distance of 6 meters because we're pushing up the ramp. But the actual load when we're finished is only going to end up 3 meters higher from its original position. So we have 6 over 3, which is 2. So this is fairly straightforward. All you need to know are the measurements of the ramp, the height of the ramp, which is this load part, and then the distance up the ramp here, I didn't write it before, I'll write it now, which is what we mean by the effort. That's where you're doing your pushing. So what this means, if it's 2, is it means that we should be able to lift something sort of twice as heavy, right? 2 times as heavy. In other words, this allows us, or we could think of it this way, it allows us to use half of the force that we would normally need to lift it straight up. So if you didn't use a ramp, let's say you had to lift something and it was 100 newtons of force, this ramp would allow you to push with only 50 newtons. But to make up for that, you'd have to push twice as far. That's how it works, right? Now, the AMA is a little more complicated because the AMA is what you actually get out of the ramp, not the ideal. See, the ideal does not involve the forces, so it's just measurements. What we're missing, of course, is the fact that when you push up a ramp, there's always a little bit of friction, which kind of robs you of some of your force. So what we need to do to calculate the AMA is we need to remember that it's usually described as the load force compared to the effort force. It's kind of the upside down version of this, right? It's the load force compared to the effort force. So the load force would be the force that you would use if you were just, actually not an equal sign, I don't like that. Let's put a little arrow. The force you would use if you lifted straight up without the ramp. Straight up without ramp. That's how we define the load. The effort is the force. So actually I should have written here straight. This is the force used to lift straight up. And down here it's the force used pushing up the ramp. Right? And these are both applied forces, the forces that you're pushing with, that you're applying. So let's put those applied, force applied, force applied. Okay, well, how do we figure out those forces? All right, well, let's think. I'm going to redraw my ramp here so we can just use it again. Something like that. And I will put those numbers back in. We might actually, yeah, let's put the numbers back in. Right? So let's put the 3 meters here. And let's put the 6 meters here. Well, okay. So for the load force, let's do that first. The load force, FL, is what you would do if you were just lifting straight up. So to figure that out, we have to imagine just grabbing the object and just lifting it up like this. So we would have to imagine a free body diagram where we were pushing straight up, lifting with our applied force, and gravity was pulling us down. And, oh, sorry, just gravity, force of gravity. Okay? So that's how we would describe the situation of lifting without the ramp. So how do we do that? Well, what we do is we do, remember our F net equation. F net equals, and this is an uppy downy sort of a vertical situation. So we have an upward applied force and we have a gravity force. All right. Let's pretend that I told you that the mass of the object was, I'll just write it over here. Let's pretend that the mass is 50 kilograms. Okay, 50, 50. That doesn't look like a 5, but it is a 5. Let's write that again, 50 kilograms. Okay, there's our mass. So F net, of course, is MA, right? And this is the F net Y. Remember, we're talking about up and down because we're just dealing with this situation that is being lifted. So F applied, and then FG equals mg. We use our little equation that we learned for gravity. Okay, now the mass is 50, but when you lift something up, you don't usually accelerate it. What you normally do is lift it up at a relatively constant speed. So when we're lifting at a constant speed, acceleration is 0. And we get F applied here. Then we have a 50 for our mass and 9.8 for gravity, but we also have to look back at our picture. The gravity force is pointing down, so we also have to tell our math that this is a negative number, downward number, by putting the negative sign, and we get 0 equals F applied minus, what's that going to be? 490. And then we can move the 490 to the other side, or we can add it to both sides, is more correct. And we now know what the F applied is. The F applied. Now this is the load force. This is the F applied for the load. It's the amount of force we've used. Remember, I said it's the force we apply without the ramp, just lifting straight up. That's how you do it. Okay, so let's now just sort of put a big black line here, and let's use the space underneath to figure out what would happen if we pushed up the ramp. Well, there's a couple of things we have to do. Sometimes you can be told what the angle of the ramp is. In this case, we're not really told what it is, but we can figure it out. So I'll do that first. I'll use green here. I want to find out what this angle is for my ramp, because I know I'm going to need that when I go to figure out my forces. So to do that, we have to look at the triangle, and we remember that the sine of theta, using our trigonometry from grade 10, is equal to opposite over hypotenuse, or 3 over 6. So that means that the sine of theta is, and theta, remember, is just a letter we use for angles. That's 0.5. And if you press the inverse sine of that, if you take the inverse sine of sine theta and the inverse sine of 0.5, you do the same thing to both sides. We unsign both sides. Well, the inverse sine of a sine is basically just theta. And then if you do the inverse sine of 0.5, you'll get 30 degrees. Make sure your calculator is in its degrees mode, not some other mode, or else you won't get that answer. So now we know the angle. So that was a little bit of a thing we had to figure out. Sometimes the angle will just be given to you, and you don't have to do that, and that's nicer. So now we have to draw a free body diagram of pushing up the ramp. So let's draw that over here. Let's draw the ramp. Let's put our object on the ramp. It doesn't matter where you put it. It's a 50-kilogram object. So this is going to look like what we did before, right? So here's what we have. We have the force of gravity on a sort of straight down. We have the normal force, which is pointing straight out like this. Then we have our pushing applied force, which is over here. Let me label some of these. Force applied, Fg for gravity, Fn for the normal force. And then, of course, we'll probably have some friction. Now, if we didn't have any friction at all, what would happen is the answer would come out to the exact same as the IMA, right? Exactly the same. In fact, we could do that. We could first do it with no friction. Let me erase that friction. And then we'll add the friction and see what happens. So let's use this picture with no friction first. Now remember how we deal with this. What we have to do is we have to resolve the gravity. We have to sort of pretend that our axis is bent to match the plane. And we resolve the gravity here into its two components, like this. And this is what we call FGX. And this is what we call FG, oh, I'm sorry, that's FGY. Oh boy, let's go back there and fix that. That's the FGY, and this is the FGX, the sideways version, okay? And we also know that if this is a 30-degree angle, if you watch the video on finding forces, you know that we can also show that this would be a 30-degree angle as well. So you can use your triangles to know that. All right. Now remember, FGY then is equal to FG, the hypotenuse over here, and this one is beside the angle, so that equals, whoops, let me fix that, FG cos 30. And this other piece down here, which is opposite the angle, is equal to FG y, which is FG sine 30. All right. And of course, we can change that to mg later if we want. So there's our complicated picture. And then we start into our FNet equations. Oops, that's a little thick. Our FNet y equation is going to look at the normal force and FGY, right? So if we go back to the picture, this red line is no longer in the picture. We replaced it with the two green ones. So our two vertical forces are the ones, remember, our axis is tilted. So our vertical forces are the ones along this axis now. Those are the y-axis. So we have the normal force and the FGY. So we run through this and we remember FNet equals MA, FN, and FGY is MGY, right? It's actually FG cos 30, so that would be mg for the FG. We turn that into mg because we know from before FG is equal to mg, right? And then we have our cos 30 there still for the y part. See, I'm using this guy right here, and all I did was change the FG to mg at the same time. I kind of did two things at once there. We have a mass of 50, but we don't expect any acceleration, so we put a 0. Then we have the normal force here. And now if I put in my numbers, I have 50 times 9.8, and I still have the cos 30 there. And again, this is a down force. If you look at the arrow, it's pointing down, so I need a minus sign. And then I just have to go and sort of crunch out that whole number. So I do that by 50 times 9.8 multiplied by the cosine of 30, and I get about 424-ish if we round it off. So 0 Fn minus 424-ish. Move it to the other side. Now we know 424 newtons equals the normal force. That's the first part of getting this force up the ramp. Then we do the next part, which is the F net x. And of course, we go look at our picture. Now, we said we weren't going to have any friction. So there's just one little force going sideways, F applied. But there's also this one, right? Don't forget, I know it looks like it's down below the picture, but that's also a sideways force. Gravity is pulling down the ramp as well. So actually, there are two forces we need to include, F applied and FGX. So we write them in, F applied and FGX. All right, again, MA. Net force is always equal to MA. The F applied is kind of what we're trying to figure out, so we'll let that ride. And then FGX is mg for the FG part. And if you look back up here, you'll see it had a sine theta in it. So we'll put the sine theta there. And again, we have to look at which way it's going. This arrow is pointing to the left, so it has to be a negative. It has to be a negative number going the other way. So we'll make sure we put a negative sign in there. And then we have our numbers. Now, again, when we push up a ramp, we don't accelerate. We push at constant speed. So we have another situation where this is going to be a 0. Makes things a little bit easier. Minus 50 times 9.8 times the sine of theta. Okay. So now we just crunch all that number out. So 50 times 9.8 times the sine of, actually 30 degrees, right? Let me put that back in here. Sine 30, we know what the angle is. So we'll just put the sine 30. I could have put it up here too, I suppose, because we already knew that. So we have 50 times 9.8 times the sine of 30, and that works out to 245. 0 equals F applied minus 245. All right. And then we move the 245 to the other side. And we get this. We should probably put newtons in there. So that's the force up the ramp. Okay? Now, if we compare, if we go right back to the start of our discussion, we said that what we want here for the AMA is the load force divided by or compared to the effort force. So the load force was way up here, 490 newtons. And the applied force here, this is the effort force. So the AMA is 490 over 245. That's the load force over the effort force. Remember, the effort is pushing up the ramp and the load was just lifting. And guess what? It equals 2, which is the same as the IMA. So we did all that work to get the same answer. But that's because we left out the friction. And if we add the friction in, what I'm going to do is I'm going to just add the friction in like this. I'm going to say there's a force of friction this way. And I'm going to tell you that the mu for that friction is 0.2. So that would be extra now in the question. So how would that change? Well, everything we did would be exactly the same except for one small change. All of this part would be the same. The friction doesn't change the load force because that's just lifting without the ramp. But the friction would come in right down here. In fact, it would change nothing over here either. This is still the same because those are the up and down forces, and friction is a sideways force. Here's what would change. We would have to add one more force in our X. See? Now we have the applied force pushing here. We have the gravity force here and the friction force. So there's 3 things to put in. That's the only change. Now, how would that change? Well, I'm going to have to write that. I can't squeeze it in, so I'm going to have to rewrite this down below. So let's just go down below and let's do that F net X again with the friction. So we have our F applied and we have our FGX, right? The sideways part. And now we also have friction. Let's see how that affects everything. This is still going to be MA. This is still F applied. This is still FG, right? MG sine, and in our case, 30 degrees. The FG is mg, and to get the x component, we did the 30 degrees. And then friction, remember, is mu Fn. Remember that little formula. So we've got that now. And then we put in our numbers, and we have 50, but 0 acceleration, F applied. Okay, now mg sine 30, 50 times 9.8 times the sine of 30. And again, if we look at the picture, that is a left-hand force, isn't it? Here it is again, down here. Lots of circles on this picture. But we can see it as a left-hand force, so it needs a minus. Now, mu, I told you the mu was 0.2. So we put that in, 0.2. We also know the normal force because we got that over here on the F, this part here. You'll notice we did this the first time and we never really used it because there was no friction. So that was kind of like not really helping us, but now it's important. The normal force, actually I wrote the answer over here, 424 newtons. So I need to take that 424 newtons and put it in here. And again, the friction force on the picture, if we go back up, look at it, here it is right here, it's pointing to the left. So that means it must be a negative as well. So now we have 0, we have F applied, we have minus. Now we've already calculated all of this right here. It was 245, so we know that's 245. But now we have this, 0.2 times 424, which comes out to 84.8. So now, when we move those numbers to the other side, we can, first of all, put them together because they're both minuses, and then move them to the other side, right? I'll do it in 2 steps so we don't get confused. First, that becomes 329.8, then 329.8 equals the F applied. So look at the difference now. That's my effort force. So if I do my AMA now with the friction, my effort force has changed because I had to push harder to get this friction. So we have the load force, which was 490, but now instead of 245, it's 490 over 329.8, and that is going to be a different number. It's going to be smaller. It's only about 1.48 or 1.5 rounded off. So the ideal mechanical advantage was 2. Without friction, the actual mechanical advantage was 2, but in reality, with friction, the actual mechanical advantage is always going to be a little bit less. It's not 1.5. That's really what we're going to get out of this because we're losing to friction. Okay. So that's the long story of AMA on an inclined plane. If you're not sure about all this stuff that we did, this math, go back and review the video on how to find the force up a ramp, because that's where you learn all this stuff. If you're jumping in here without watching that video, this is going to look all crazy, but that video will explain that in more detail. So that's how you do the AMA for an inclined plane with friction.